Hey guys, so I'll be doing 25A. So here we have a house with a ladder leaning against it, the ladder being 25 feet tall, and the top of the ladder moving down while the base of the ladder is moving outwards. So let's just set up the formula for it right now. So we have the base ladder x squared plus y squared, the height created by the ladder leaning against the wall, and the actual ladder itself, which I put h squared to denote hypotenuse squared. However, only x and y are changing. H, the length of the ladder, remains constant. So the actual equation is x squared plus y squared equals 25 squared, which is 625. Now, the problem also gives us the fact that the rate at which the base of the ladder is increasing, or the bottom of the ladder is going away from the wall, is 2 feet per second. So we can say that dx, or the derivative of x with respect to time, is 2 feet per second. Now, we are given 3 different lengths for the base, and let's just go ahead and solve each one of them. So first, let's set up the derivative. It would, in using implicit differentiation, of course. So it would be 2x times dx over dt plus 2y times dy over dt equals 0. Now, dx over dt is given to us, and in this they give us 3 different lengths, and the first length is 7 feet, x equals 7. And so we can solve for y. X squared plus y squared equals 625. So then x squared is 7. It will be 49 plus y squared equals 625. And so y will equal 24 using basic algebra. Now, we have the derivative of x with respect to t, we have the value of y, and we know the value of x, which is 7. So now we can solve for the rate at which the ladder is going down the wall. So 2 times 7 times 2 plus 2 times 24, and we are solving for the derivative of y with respect to time, equals 0. And so, using basic arithmetic and algebra, we can solve the derivative of y with respect to time is negative 0.583 feet per second, or negative 712 feet per second. So, the ladder is going down the wall. Oh, I'm sorry. When the base length is 7 feet away from the wall, the bottom of the ladder is 7 feet away from the wall, the derivative of y, which is the top of the ladder going down the wall, is negative 0.583 feet per second. Now that we know this process, it becomes fairly simple to solve for the other base lengths. For example, so x equals 15 feet away from the wall. Let's just use the same exact thing that we did here. So x squared plus y squared equals 625. X squared is 15 squared, and 15 squared is 225, so minus that from 625, and we get 400. Solve for y, and that becomes 20 feet. So now we know the length of y and the length of x. We can now solve it the same way we did in the first base length. Okay, so we 2 times 15 times 2 plus 2 times 20 times dy over dt equals 0. Solve for the rate of y, and that will be negative 1.5 feet per second. So when the base length is 15 feet, the rate at which the ladder is going down the wall is 1.5 feet per second. So now we're going to do the rate of y if the base length is 24 feet. X equals 24. Same process. X squared plus y squared equals 625. And it's 24 squared plus y squared equals 625. Y squared will equal 49. And y will equal 7. Let me just flip this over. Okay. Sorry about that. Okay, so then, yeah, it's the same process as the other two base lengths. 2 times 24 times 2 plus 2 times 7 times dy over dt equals 0. Because when x is 24, y is 7. And then solve for the rate of y using basic arithmetic, and the rate at which the ladder, when the base length is 24 feet, the rate at which the ladder is going down the wall is 6.857 feet per second. Okay, and that is 25A. Now moving on to 25B. The ladder in the wall is changing when the base length is 7. So first, let's set up the equation. The area of a triangle, that is. Area equals 1/2 base times height. And I'll just change base and height to x and y, as we know them from the previous 25A. So area equals 1/2 x times y, which is basically the base and height of the triangle. So now that we have this, let's find the derivative equation. So it'll be the rate of the area, dA over dt, times, and this one will be using product rule of differentiation. So it'll be 1/2 x times dy over dt plus 1/2 y times dx over dt. Okay, and it's when the base length is 7. So from 25A, we already calculated the rate of y when the base length is 7. The rate of y is negative 0.583 feet per second. And we know the derivative of x, which is a constant, is dx over dt, is 2 feet per second. So we know the rate at which the ladder is going down the wall. We know the rate at which the ladder is extending away from the wall. And we have the values of the base and the height. We calculated y in the first part of 25A. When x equals 7, y equals 24. And now we can just plug it all in and solve for the rate of the area. So it'll be 1/2 times 7 times negative 0.583 plus 1/2 times 24 times 2. Using your calculator and solving this, we will get that the rate at which the area of the triangle formed between the wall and the ladder is changing is 21.958 feet squared per second. So when the base length of the ladder is 7, the area formed between the ladder and the wall is increasing by 21.958 feet squared per second. Okay, now let's do 25C. 25C. So the last 25B we worked with area. 25A we just worked with the rate of sides, and now we're going to find the rate of an angle. So this asks for the rate at which the angle formed between the top of the ladder and the wall is changing. So let's just draw this out first. So it's this angle right here, theta, and it's when the base length is 7. And we always know that the length of the ladder is always going to be 25, and when the base length is 7, y is 24. Okay, so now let's find the equation that we're going to use. So let's do, well, we have, we could use cosine or sine, but in this situation, I'll just use sine. Say sine theta equals, and though it says 7, the base length is always changing, so I have to put x right there over the hypotenuse, which is a constant, so it'll be 25. So when the base length is 7 at x equals 7, we already found in 25a dy over dt equals negative 0.583 feet per second, and dx over dt is always 2 feet per second. It's just something that we should know. And so, okay, we have this equation, and let's solve the derivative for it. So the derivative of sine theta is cosine theta, and remembering chain rule, times the derivative of theta with respect to time. And this, with x over 25, we have to use the quotient rule of differentiation. So it'll be, oh no, sorry about that. No. 1 over 25 is constant, so technically I just have to find the derivative of x, which is 1, but also remembering the chain rule, which will be times dx over dt. Sorry about that. So this is our derivative function, but we already know dx over dt. And we already know theta because we can just solve for theta right there. Sine theta equals x over 25, 1x equals 7, so sine theta equals 7 over 25, equals the arc sine 7 over 25. When the base length is 7, theta is 0.284 radians. Plug that back in. 284 times derivative of theta times 1 times over 25 times the derivative of x with respect to time, which will always be 2. And now that we have all these values, just solve for d theta over dt, which is 0.0833 radians. Oh, well, sorry about that. 3 radians per second. And